everybody for attending. Our speaker and candidate today is Banafsheh Ferdousi from the University of New Hampshire, where she is a research scientist. Dr. Ferdousi got her Bachelor of Science in Physics from Azad University in Iran. She is no stranger to Texas, having received her Master's of Science in Particle Physics at Southern Methodist University in Dallas, and received her PhD in 2017 at the University of New Hampshire in Durham, New Hampshire. After that, she was a postdoc with a joint appointment at Boston University and the University of California, Los Angeles from 2017 to 2019, and now is a research scientist at the University of New Hampshire. She has a broad interest in space and magnetospheric science, studying suborbital polarization streams, analyzing both model and simulation results, and very interesting to me is just now getting started in learning more about geomagnetically induced currents. So with that, Banafsheh, I'm going to hand it over to you, and if anybody has questions, if you could press the raise your hand button on the bottom of your screen. If you wiggle your mouse, the menu will come up, and we'll try to interject as things go. So yeah, go ahead.
Yeah, sure. When I start drawing the PowerPoint, I might not see people raising their hands. So if you could just tell me, Banafsheh, just stop, or or we move have all the questions towards the end, because it would be So let me know how does it work. Yeah.
You bet.
So okay. Thank you, everyone. Thanks, Dan, for the introduction. Yeah, I'm Banafsheh Ferdousi. I usually go with Banafsheh, and I'm currently research scientist at the University of New Hampshire. And my work mostly been on coupling phenomena between magnetosphere, ionosphere, and thermosphere. And so today I will give you some of those phenomena that I worked on. So here, the outline, I noticed that physics department in UTA is a very nice, diverse physics community. So I would give a little bit more description about these terms that I'm going to use through the talk, and then I will talk about the model that we have, and then I talk about some of the research and some of the research topics I've done. For example, signal propagation time from magnetotail to the ionosphere, and auroral streamers and their relation with Bersty Buck flows, and the relation of the SAPs with subauroral neutral winds, and this topic that Dan was mentioning, this nice GIC that I'm very interested now to pursue. And finally, I would give some ideas how I could contribute to CUSIA. So basically, what you see here, this is just illustration of the Earth magnetosphere with the sun, of course, in the left, Earth here, and this is ionosphere. So basically, I remember when I was a kid, everyone was saying, oh, the space is empty. But then I noticed, no, it's actually not empty. The space is full with these charged particles that's originated from the sun and travel all over the solar system, including Earth. And when these solar winds encounter Earth, as a result of the interaction between the Earth magnetic field and solar wind, these cavity forms around the Earth that we call magnetosphere. So magnetosphere would be this whole system, and the day side usually is we call it here magnetopause, that is towards the sun, and magnetotail that I'm going to use a lot of this term is on the night side. Basically, it's from the Earth all the way for a long distance. And as you could see here, these field lines are all get connected to the Earth, and basically through the ionosphere. So you could see these on the right side, top side pictures, and they these field aligned currents are the ones that connects basically magnetosphere to the ionosphere and could accelerate particles and electrons towards our ionosphere. Basically, that's why we see the aurora, and that's one of the phenomena of the magnetosphere, ionosphere, and solar wind coupling. So having said that, I'm going to jump right into the model. And so we have MHD model, and it's kind of similar in some ways to the physics of it, similar to SWMF, Batsaros, and LFM. And it's the first part is the MHD part is Open GGCM model, which is basically these you see these 3D plots on the right. It's solves MHD equation for single fluid. It's basically solves set of the hydrodynamic equations and Maxwell's equation. That's why we call it magnetohydrodynamics. And it conserves plasma energy, and for the ionosphere part, it solves potential on 2D spherical grid. And so basically how our model works, we have all these, we have solar wind monitors at the Lagrangian points between Sun and Earth. And they could give us information about solar wind. For example, what are their velocity, their temperature, their density, their magnetic field. And with that input, we would implement them to the model, and we are able to run the model, for example, for certain events, and be able to see those events. And another part of the model is the model later what got coupled with the Thermosphere-Ionosphere model, which is chemical photochemical reactions, and it determines the conductance, and the main inputs it gets from the are field aligned current and auroral precipitation. Another part of the model is the Rice convection model, or RCM. Basically, the MHD is kind of approximation and works at in the magnetosphere. But when we get closer to the Earth, there are some kinetic physics involved that shows the motion of the particles, and to account those drift motions, we couple the model with RCM model to have better physics of magnetosphere, to more complete physics of the magnetosphere. So on the right, it's the diagram of we couldn't make it more complicated than this. It's the diagram of showing how the models our coupling methodology work, how basically they feedback each other. For example, from Open GGCM to ionosphere, Open GGCM sends density, pressure, and precipitation, a field around current, and receives potential from the ionosphere. And with the RCM ionosphere coupling, RCM again receives potential and sends field aligned currents basically for the low latitude region. We call it region 2 field aligned current and auroral precipitation. And we blend these precipitation with MHD precipitation higher latitude. And RCM and Open GGCM are a little bit more complicated. It basically converts flux to content to pressure and density, and receives MHD pressure density at boundary. So given that, I jump into the results. So here is one of, I think it was my first paper as a PhD student, as I worked on signal propagation time from magnetotail to the ionosphere. And actually, this figure of my paper made it to the cover of July issue of the JGR. That was when I was PhD student, that was very exciting for me. And so I would like to give a brief introduction why I'm doing that. as I described earlier, sun constantly throws these charged particles, or otherwise known as solar wind, through the solar system. And as these solar wind encounters Earth's magnetic field, it opens the already closed field lines, and it stores its energy and momentum into the magnetotail. When this energy becomes very high, the flux becomes very high, it cannot hold it anymore. And you saw that triggering, and that accelerated most of the particles towards the ionosphere. So that is called auroral substorms. So these phenomenon we already know about the substorm for a long time, but we know about the physics of it. How does it work? But the main question in our field, it's like we call it 5-decade old mystery, is what is actually the trigger of the substorm? So the problem with the substorm is that everything happens so fast. They happen in, like, they call it 2 minutes problem. Everyone happens so fast that you don't know which problem happens first and which problem happens second. For example, there are these two models. These two models are the most established models. The NEL model, which also calls outside in, they say basically some sort of reconnection happened in the midtail, and that made like these fast flows move towards the Earth, made the Earth field more dipolar, and that created new current accelerating electrons toward the ionosphere. And the other model, the current disruption model, there you see the physics is the same, but they say instead of happening in the midtail, something happened close to the Earth. Current somehow got disrupted, and that created this substorm, and that sent the refraction waves towards the reconnection site. To solve this controversy, in 2007, this Themis mission was launched. It's basically consistent of 5 identical satellites that orbit around the Earth. And when they are at the night side, the magnetotail, they line up somehow that they could see different signatures of the substorm simultaneously at the same time. So we would be able to solve this mystery. And interestingly, like the first paper came from this satellite from this mission was with Vallis, Vasilis, and Gelopos, and he said, yes, I found that the tail actually is reconnection is actually the trigger of the substorm. Of course, their competition, Anthony Louis, came and said, no. The same event, he came up and said, no, that current disruption actually happened, the problem. And so still the results from the Themis were controversial. And to be honest, 13 years later, people are still yelling at each other and saying, no, that caused it, or that caused it. And there's all these new event models. But I want to just how I'm involved in this. The problem with the NEL model was that they said disturbance from the midtail cannot travel that fast to account for the trigger of the substorm. So that's where my works come into place. So for that, I want to study MHD wave travel time. And basically, they're important because these MHD waves carry energy between different regions and play a key role in transport of signal from the magnetotail all the way to aurora. The previous work on this are done by, for example, by Chi et al., that they used the empirical values of density and temperature, and they gave a wave a restricted path and realized how long does it take for them to reach the ionosphere. As you see, for example, for this -25 RE, it takes 200 seconds. That's completely, it cannot account for the NEL model. And the same goes with the Lin et al. Study, but I'm not going to details of that because it would take lots of time. go on to my study. So by using the model that we have, we actually could have launch waves by ourselves. On the right, you see the plot of in the magnetoton. Here is the night side, here is the day side, and basically I created two runs. One with perturbation. By perturbation, I mean I interrupted the plasma pressure in the plasma sheet at x minus 25 RE, and then I launched this sinusoidal wave. I wanted to see how these waves are traveling. So the physics of that is basically simple, because I clap my hand, you hear, because I changed the pressure in the room, that launched wave. We did almost the same thing, kind of same idea. And here is the wave is launched. As you could see, the waves are going actually towards the lobes of the magnetosphere, and then through the plasma sheet, and all the way through the ionosphere. So how this is and I will show this is faster than previously thought, and why is faster. Basically, the thing is that for our model, with them we having this global self consistent model, the wave path is not restricted to the any certain path, and the magnetic field values and density are determined self-consistently. So what we saw that the waves are actually travel faster through the lobes, and they come to the ionosphere, whereas there's this path, the waves travel slower through the plasma sheet and then travel through the field line. I went to the ionosphere and see what is the arrival time of these waves. On the here you see delta field align current. Basically, I again subtracted that two model and saw when does these waves arrive, and with having a certain threshold in magnetic field perturbation as well. So what I noticed, when the wave was launched at x minus 10, it took 30 seconds, and it was when it was in the x minus 20, 45 seconds, and in the midfield around 72 seconds. And that is the remarks of the signal travel time. So the waves travel faster than we thought. It takes about 70 seconds, and that actually could account for the NEL model. And the reason why it's different from the previous studies is that we didn't constrain the path of our wave to a certain path, and our model determines those magnetic field and density value self-constantly. And so every topic that I will talk about, at the end I will give a future plan, what I can do at UTA regarding on that topic. One of the interesting thing about this topic is that this travel time can be used in the magnetoseismology area. Basically, it's kind of like seismology, or with knowing this with having some information about the waves, we could infer the source location and start time of the impulse. And for my part, I have to launch these waves again during different geomagnetic conditions, and study how they could be affected, for example, by Bercy bulk flows, by substorms, by storms, and that builds a opportunity for developing this magnetoseismology model. So moving on to the next topic, I also did auroral streamers relation with Bercy bulk flows. Okay, and the reason behind that is that so magnetosphere and ionosphere, as you see here, they are connected through these complicated, complex current system. And everything, especially when we have in the magnetotail, we could see like a TV, we could see some projection of that in the ionosphere. The advantage of the ionosphere is that we have all sorts of measurements. We have all sky cameras, we have radars, we have aurora images, we have ground magnetometer. Whereas in the magnetosphere, the measurements are sparse. They are like limited to the single point. And so knowing the relation between these dynamics and the ionosphere, we are able to remote sense the tail activity. And so what do I mean by bursty bulk flows? Basically, bursty bulk flows, they are short-lived, high-speed plasma interpreted as plasma bubbles. And they are important for our magnetosphere because they carry 60 to 100% of energy and momentum through the ionosphere. So in the bottom, you see how these BBF illustration of these bubbles. So they are like they are low entropy fast flows that are moving towards the Earth. As they start to move, the depolarization front forms in front of them. So that's one of the reasons we could detect them in the observation. This is the signature of the BBF. Also, another thing that happens because of the movement of these BBFs, it creates shear between the BBF and its surrounding. That shear creates vorticity. Through that vorticity, field around current happens and maps to the ionosphere. This is kind of similar to the substorm current wedge. And so basically, we could see some phenomena in the tail. We could see their foot points in the ionosphere. So what are their signatures actually on the ionosphere? These phenomena called polar boundary intensification. They are basically intense transient auroral disturbance initiated around the magnetic separatrix and extend equatorward. So here are some previous studies. This is by Zesta et al. It's from image satellite. Basically, these are the PBIs she saw, and based on previous studies, they mapped everything from the ionosphere to magnetotail. And as you see here is the foot point of the geotail. You see we have all these nice aurora, but we have one point of measurement. If we are here, we miss this BBF. And but the limitation with the challenge with this approach is that there's so many limited coverage in the tail, especially in the azimuthal direction. And with the mapping of backward from ionosphere to the magnetotail, they were using these empirical models, Sigonanka model, and sometimes these models are averaged over the magnetic field, so they might not be reliable on the stretched magnetic fields. During the substorm, the tail is completely stretched and the fields are twisted, so we cannot exactly make sure these results are correct. In the site with Dr. Zesta, I started doing the same project on using our model. So here is the solar wind during that event. Is there is a nice BZ, there is this nice substorm as we see in the AE index, and here is the substorm signatures from Rankine Intel Meridian scanning photometer. Here is diffuse aurora, here is the discrete aurora. What they noticed that substorm happened actually at 2:30 prior, before they could see in this scanning. That was they cite as the PI2 pulsation on the ground. So I got the same event. As I said, I feed the model with this solar wind data, and here is OpenGGCM result. On the left, you see the discrete aurora. On the right, you see the diffuse aurora. So from the top to bottom, they are located at different MLT. MLT 21 would be almost pre-midnight, we call it, and MLT 0 would be midnight, and MLT 3 would be towards the post-midnight and towards dawn. So what are the signature of the substorm that we make sure, this is, if we see in the model, this is substorm, is that some intensification should start in the midnight, and they should propagate both like towards dusk, westward, and then they should propagate equatorward, and they should expand poleward. So saying that, comparing that with the observation, we get the substorm onset in our model, but it's slightly at earlier time at 150 UT. So let's see, like with this aurora, what happened in the tail. On the left, you see the diagram for magnetosphere, as Earth is here, and the color shows the BZ, and these green contours shows the BZ0, basically the tearing mode of the magnetosphere. And as you could see here, this is by near Earth neutral line model. We say there is some sort of like reconnection happening close to the Earth, and these like arrows showing the fast flows. As you see here, before the reconnection onset, there was like this small like tearing, but then the nearest ennial happened, and it shows so many BBFs are coming towards the Earth. And I also, so yeah, that's very nice BBF. And on the right, I have the plasma pressure, and then with contours, the black solid contours are the earthward motions, and then with the dashed lines, there are like tailward motions, BBFs. And to confirm that these BBF have characteristic of BBF that we see, I put virtual satellite at different location to make sure they have like a BBF characteristic. On the left, this is like a regular BBF signature. There is an enhancement in the velocity. On the right, you see it in the model. So there is this enhancement. As I described, every time there is a depolarization because of their movement, flux piles up in front of them. So we have to see sharp enhancement in BZ. We see it, and they are mostly associated with density drop, and we would see all these signatures. So confirming that our model gets like a decent BBF, we could move on to the next level. So basically, on the next level, I try to map everything from the magnetotail to the ionosphere. The reason for that is because the ionosphere resolution cannot resolve these these streamers, these PBIs. They are like very narrow. With the resolution that we have, we cannot see. But with mapping, we have the opportunity to see that and actually do one-to-one correlation. So I run this model basically like if you see this one here, this is the signature of as a streamer here. If you see this BBF here, that shows up here, and you see all sort of motion of the streamers that are being run through this BBF. And that gives us an opportunity to remote sense of the magnetotail, basically. So basically, the remarks of this work is that this study provides an opportunity for remote sensing of the magnetotail activity, because we know if, like, for example, what shape of BBF creates some shape in the ionosphere. For example, if like they are in the dawn, they would have like some sort of eastward orientation. If they are towards the midnight, they would have like some sort of north-south structure. Also, another important outcome from this result was that there was this new theory of substorm, that intrusion of these streamers could create the substorm, and we saw not necessarily that happen all the time to our model. So here is the future plan I really would love to follow at UTA. It's I'm looking forward to improve our model through machine learning. So these substorm phenomenon that I said, it's not always easy to get with the model, because they depend on so many parameters, like resistivity of the model, like the precipitation, like even the grid resolution could completely change the nature of this substorm. With machine learning technique, we have the ability to give we have these certain runs that is working, and say these parameter, how like go and change this parameter and run the model multiple times and come up with a solution to find a substorm. And actually, we my advisor and I we submitted the step one of this proposal to DOE. And also another interesting topic this involves is that, as I said, there are so many satellites and magnetotail, but they have like one single point measurement. But if we use machine learning technique to go to survey all these BBS through different satellites, MMS went to the night side, and Themis and cluster, we are able to have like some models of these BBF and compare them with ionosphere features. And we could do the same thing with the modeling. We run the model like multiple times, many times, and sum up the statistics of these empirical these statistics of these BBFs, and create a simplified empirical description of BBFs and streamers. So that's one of the topics I'm really interested to follow. Okay, now switching gear to completely new direction. So there are these another phenomenon that are associated with magnetosphere, ionosphere, and thermosphere coupling are called SAPs. SAPs are like, from their names, they are like, I think the best describe them. SAPs are basically these subauroral polarization streams. So they are below the aurora, and they are like these fast ion flows that have northward electric field. In this picture, I think that it shows the SAPs very perfect. I chose this picture. It's from Millstone Radar Hill, and on the y-axis shows the velocity, and then x-axis shows the latitude from 44 to 66. Auroral oval is here, and then this shows the density. So basically, they would happen with enhancement in ion drift, westward velocity, and they are usually associated with trough, and they are below auroral region. And so to study this, this was my postdoc study. I used a different model. It's called CTIP-E-RCM. It basically has the ionosphere and inner magnetosphere part, but it's missing the MHD part. And for the MHD part, we use empirical model for precipitation. And also I use the DMSE satellite, which is a defense meteorological space status. So sorry if I don't pronounce it right. And we compared the results from DMSP with GOCHI, which is at the lower altitude. Basically, DMSP would give us plasma density, precipitation, and ion velocity at 800 altitude. And with the GOCHI is at the lower altitude, it's around 270 kilometer, and it gives us information about neutral wind density and their velocity. Both of these satellites were kind of at the same location, covering the MLT 18 and 20. So they were covering the dusk region. This area is the area that we usually see the SAPs. And for the simulation, as I said, I use this CTP RCM model. And so here on the right, you see the plot of IMFPZ. This is during the St. Patrick's 2000. Sorry, I didn't put the timing there. It's during the March 17, 2013. Yes, it's during the St. Patrick's 2013 events. We have like this nice storm, and we wanted to see like how could we see the SAPs in this DMSP. On the middle, you have the ion density, and then here you see the panel E shows the ion velocity. Basically, auroral oval would be around here. We know this from like a precipitation plots that I didn't include it here, and SAP happening below that area. And what I noticed, like, and what everyone noticed, usually before, like, previously everyone was thinking SAPs at the magnetosphere coupling phenomenon, but like recent studies, including you, I think she has lots of nice paper about that actual thermosphere plays an important role on SAPs as well. So we noticed that neutral winds have similar behavior of the SAPs with 2 hours delay. So I'm going to talk how actually these SAPs can accelerate and how much the thermospheric wind feedbacks to the ionosphere. So on the left, you see the simulation from the CTP RCM, and this is comparison between the ion velocity of our model and observation. We get like these nice two-band features. We get you see with the peak of the storms, deep of the storm. We usually get peak of the storm, but here shows the deep of storm. We have like this enhancement in the ion velocity, and the same happens to the model. And with the neutral wind, we get the same features. I also got a little bit deeper and then tried to put again like virtual satellites at the location of this phenomenon, for example, at 7 different times, and saw that how our model how our model could be compared to the simulation. This red is data from DMSP observation, the blue is the simulation, and the black dot is the quiet time. As you see through, there is a good agreement between model and simulation for both wind and for both ion drift. And so we, like with this level, we would say, okay, we have like some sort of successful we were successful in reproducing overstructure of the SAPs and winds, and we could move on to the next steps and do like physics behind it. To understand how actually these SAPs accelerate the neutral wind, we use this neutral equation of the motion that has different force terms like ion drag, Coriolis force, and horizontal advection and pressure gradient. I color code them so you could see how they are related. And as you see here, the ion drag has the most important effect on accelerating SAPs compared to the Coriolis force and horizontal advection and pressure gradient. That was interesting because at that region, like usually SAPs are, we call it low density region, and you see the ion drag term is like multiplied by density. So basically the difference between the velocity of the ions and neutrals create this acceleration. Basically neutrals are sitting there and ions dragging them to their direction. And this happens other way around. I'm not going through to that details because I think I'm running a little bit late. And another thing I've done, I did with this work, so with the modeling, we have the luxury of being the king, of the nature. We can turn off a knob, or we can kill a parameter and see what happens, and we are able to study the physics behind it. So I ran two models, one having the neutral wind and one not having the neutral wind. I wanted to see what is the effect of neutral wind on SAPs and on the IT system. And with the SAPs feedbacks we saw in the field aligned current, there was enhancement by 20% in the equatorward region of the SAPs. And with the ion drift velocity was actually high. Here is, sorry, I didn't describe here. This is run with the wind. This is without the wind. This is their difference. And we noticed that their ion drift increases by 30 to 40%. So wind basically amplifies magnetosphere-ionosphere coupling process. So here are quick remarks that I mentioned. Ion drag is the main force driving the neutrals. Neutral wind exhibit the flywheel effect equatorward of the SAPs. And then wind feedback has strong effects on magnetosphere-ionosphere-thermosphere coupling process. And here are the topics that I would like to further investigate. Actually, this is my ongoing project at UNH now. We are using OpenGGCM, RCM, CTEAM, and I will later describe we are trying to implement the new model to understand SAP's fundamental problem with the SAPs. Also, I would like to understand the relation of the SAPs to different solar wind drivers by running a large number of runs and surveying how these features, how these SAPs changes with different solar wind parameters. Also, another interesting thing that people are recently been seeing, they are seeing these fast flows, and then that looks like SAPs and happens quiet time. So far, we were all seeing SAPs during the geomagnetic time. So are they SAPs or not? So I'm very interested to investigate more on that. And so here is the new topic that I'm working on. I'm looking forward to working on, and I think Dan is very expert on that. And it's are called geomagnetically induced currents. And basically, those are the phenomenon that actually could affect our everyday life and could harm our infrastructures. And so they could induce current to the power system, to the pipelines, and create a long time blackout, and then distract our GPS system. So it would be a very interesting and important to predict them weather prediction scenario we have. Like we want to be able to do space weather prediction. With this modeling, we are able to do that prediction capability. and I wrote a proposal for that. It's when I wrote it as a research scientist to cover most of my salary, but I think might be enough for 1.5 graduate students. For half a graduate student at UH is definitely enough, but I hope it would be for another graduate students at UTA for at least 3 or 4 years. So what are these GIC? They are driven by geoelectric field through Ohm's law. They happen during geomagnetic storm times, and they are related to the ground magnetometer through Faraday's law of the induction, curl of E dB dt. So why this is important? Because with the ground magnetometer and with the models, we are able to determine dB dt. So here is some work has been already done at NASA that when they were going to select a model for the SWIPC Center, and so this is the black is open GGCM and the blue is observation at high latitude ground magnetometer, and basically I should say that with doing some probability of detection, if the model actually sees the signal, and probability of false detection, if model sees the signal but there is no signal, they were able to say that MHT models have the overall capability of capturing characteristic of dB/dt, and in comparison to the empirical models. And then after this result, I think SWMF was adopted at SWIPC Center for the prediction capability. And GIC, it's not only depends on the magnetosphere-ionosphere current system, but also on the Earth's conductivity. For example, if we have high resistive volcanic or granites, like the area that I'm living in, New Hampshire, we have lots of granite. So these resistive rocks cause higher geoelectric field and are probably more affected by these GIC, whereas the low resistivity rocks such as sedimentary, they are containing significant amount of water, and they could create low geoelectric field. So it's important to know what is the structure of the Earth is to better predict these GIC. Sorry, here is a little bit crowded, but basically we get this dB/dt either from the MHD model or from the ground magnetometer model with this MT surveying technique that is provided by USGS. They could give us Earth impedance, and having that, we could get geoelectric field. Knowing the geoelectric field, we can give this to the power companies, and they could integrate them over the power lines to determine the voltage. And for that, I'm going to use the BestPy. It's open software created by one of the scientists at USGS, and would like to determine the geoelectric field and to be better predict the GIC. I did some early works. I think I have 46 minutes. I would go quicker. So this is basically shows the different ground magnetometer stations. The size of the circle shows the enhancement. So if the circle is bigger, that mainly means that there is a stronger activity. So here is long before the storm, and now it's just during this 6:30 sudden commencement of the storm, there is lots of activity. As you see it through the storm, these activities, the intensification and their location changes. You see, so far most of the studies only focused on just knowing for certain event we see certain signals, but within the same storm you see all these sorts of activities. So it's important to understand what happens through the just storm. And I did simulation with OpenGGCM for the same event, and and then what I've noticed is that these, we a little bit underestimate these ground magnetic perturbation. That's mainly because maybe we use some sort of approximation to determine the GIC. Another interesting I noticed is that these DBDT are very localized. Just using a single satellite like next flood, just using these signal satellite, we might miss the location of actual DBDT. For example, we see the observation sees something and the model does not see it. We punish model because we're not seeing it. So it's important to have a better prediction of and better measurements of the model capability. And here are some of the questions that I proposed through my proposal. I want to understand GIC under different geomagnetic conditions, like CMEs or CIR, how they differ. And as I showed you, during the same storm, these GIC changed a lot. And I want to see, for example, what happens at ring current enhancement, what happens at the sudden commencement, and distinguish their differences. And beside that, I want to understand the physics behind that. What are the currents that are responsible for GIC for different phenomena? For example, for substorm, is it the night side? Probably substorm current, which has a contribution. On the day side, it might be other contribution. And I also, another important thing is that, as I said, as I forgot said, this GIC could be really, these geomagnetic storms could be very strong. Like, for example, there was this Carrington event that it happened many years ago, before this modern era, and it interrupted all these telegraph systems, and they went through fire. So it's important to test the model and to see how the models could predict these stronger storms. And now it's time for Kusia. So here is my my contribution to Kusia. It would be to adding a new global MHD model, OpenGGCM, RCMC team, and probably sooner IPE. So here is some of the possible source of interhemispheric asymmetry that I adopted from Dan's CAMP table. There are different sources, like primary source, offset and tilted of magnetic field, seasonal, diurnal style differences, and interplanetary BX/BY. With our model, we are able to capture most of these things, and with the new model I would describe, we would be able to solve these offset problem as well. There are also another secondary sources are asymmetry of ionospheric precipitation and conduction and potential. In my SAPS project, I'm trying to, because of SAPS are really related to the precipitation, so I'm trying to correct and make mother's precipitation better. So I think that would be very useful to this project as well. So when I was a last year PhD student, I get very excited about different topics. I did this as a side for my own curiosity, see how is the effect of actually these IMF-BY on these bursty butt flows, how could change these fast flows. And now it's coming to the interhemispheric asymmetry. Those again became important because I could do the same thing in the ionosphere. Basically, what happens when IMF-BY creates asymmetry? As you could see, this is very maybe it's very a little bit naive, but I like it because it shows the concept of what happens with these effects of IMF BY in the magnetosphere. And so to understand how this BY could actually affect the asymmetry, we have to understand forces acting on the field lines participating in Dungy's cycle. And basically what happens, magnetic tension forces on the newly opened field lines will point in the opposite direction in the two ends, as you see here, and affecting the magnetosphere differently in the two hemispheres. For example, IMF BY positives move magnetic flux from the northern hemisphere to day side dust, merging side toward the northern hemisphere, high latitude on the downside. And the same procedure happens with IMF BY negative, have different effects. So for that, I had these generic runs. By generic runs, basically, I mean I put the dipole tilt to 0, so I do not see the effect of like dipole tilt, and I ran the model with different clock angle. By clock angle, I mean like keeping the total B constant and changing BZ and BY to certain values. Especially what is important to see the effect of positive BY and negative BY during negative BZ. So I ran the model, and here is on the right you see ionosphere convection, and this is earlier in the run. As later you see in the run, during the positive BY, we expect to see this banana shape, they call it, in the downside, and orange-like shape on the dust side. That's just kind of showing that like the model has the ability to capture these physics. So I plotted different parameters like joule heating, field aligned current, for example. You see some sort of asymmetry between. So on the left column is the northern hemisphere. On the right is the southern hemisphere. The same goes with the field aligned current. As you see, there are some sort of asymmetries for different parameters in northern and southern hemisphere. That's just basically just was for my own curiosity and see the basics of the model works. And this is again this is our model: OpenGGCM, CTM, RCM. So we have like some nice utilities. We have this visualization package in Python that is called Visit. Like when I was a PhD student, my friend and I he was the main developer, and we tried to get this visualization so we all have the same software to do our visualization in Python. That is in GitHub, and it's accessible, and people are welcome to help to better to the contribution, better develop it. And we have OpenGGCM wiki that gives more information about the OpenGGCM. We have like this collaboration part that we usually, when we're collaborating, we like put our results there, and we talk through there. And so we have these nice utilities for us. And I would like to tell you about the development of OpenGGCM that I am involved with. There are other developments, but these are the main ones that I'm involved with. The first one is we are coupling up OpenGGCM, RCM. We're basically replacing CT model, the coupled thermosphere-ionosphere model, with IPE. It's ionosphere-atmospheric electrodynamics model with and whole atmosphere model. And this is ongoing project with NOAA and SWIPSI Center with Tim Fullerwell and Naomi. Many people in our space physics know them. And also OpenGGCM is part of the AIDA, Artificial Intelligence Data Analysis Center, that is in Europe, and it's a combination of different universities in Belgium, Italy, US, and they're trying to develop a software called AIDA pi to be able to replace basically a future ideal. And our contribution is we do data assimilation for OpenGGCM. I do like some sort of consulting with them, and I help them with them on that part. And another part of is important that I would really love to get to with my new, if I get my new proposal, is just using the information from OpenGGCM, feed them to these empty data, and be able to predict the GIC. And so I briefly talk about the IP and what values that could bring for the CUSIA and for the asymmetric center. So basically, IP is the same set of equations of CTIM, but they replace the magnetic field model with realistic IGRF, Earth magnetic field, and so it wouldn't have the offset problem of the magnetic field. Also, there is no artificial boundary between low and high latitude, and that allows for the plasma transport between different regions. As you see on the left, you have the total electron content for the phenomenon called TOI, basically tongue of ionization, with comparison with observation, and nicely model could capture. With CTIM, we were not able to get these features. Another important thing is much higher resolution of the CTIM, and another thing I'm very interested is that I've been involved is to see effect of wind dynamo. Even with CTIM, we have the wind dynamo, and I was talking earlier. These neutrals could be another source of. This neutral also could be another source of asymmetry because they are seasonal and diurnal dependent, and it could drag ions, and they could produce asymmetry. I'm very interested to see their effects on the asymmetry. Another important part of the new coupling is using this whole atmosphere model. Basically, it will be the first model that we will simulate everything from the solar wind all the way to the atmosphere, and it allows for the response from upper atmosphere to the ionosphere. For example, would be this interesting for the asymmetry center is that, for example, if weather activity, if hurricanes happen over the Rockies, they might launch these gravity waves that import energy and momentum to the thermosphere and ionosphere that might create new source of asymmetries. So that would be interesting topic to follow. Saying that, some of the topics I would like to investigate in asymmetry center is dependence of asymmetry on solar wind and geomagnetic activities. Those are the area of my strength. I've worked with a lot with them. And also, does the neutral wind dynamo contribute to interhemispheric asymmetry and in MI coupling? Finally, so with the CUSIA Center, I think if OpenGGCM comes alongside with SWMF and LFM, we will be the first center that will have all these high-resolution global coupled model at the same time. It allows us to understand the physics of asymmetry better and verify it with multiple models and without limitation of each models. And also it creates collaboration opportunities for model development, of course, for new proposal opportunity. So I'm very excited to share our model and get feedbacks from the other modelers and improve all our models together. And thanks for your attention. And if you have questions, I will be happy to answer.
Okay, thank you, Bashi. If anyone has a question, raise your hand and I will unmute you. Do not unmute yourself, or I will mute you. Okay, Dan, you have a question? You can unmute yourself, actually. Dan, go ahead. You have to unmute yourself, though.
Sorry, Microsoft Teams is fighting me today. It keeps, yeah. So going back to your conclusions on the section on SAPs, do you expect? Yeah, way back up there. So sorry to make you.
No, it's okay.
Yeah. I thought this was very interesting, the effects of neutral winds and everything else. But I'd be curious to, just to have you speculate a little bit on how big of a factor these effects will be, or how much these effects will change when we start to introduce interhemispheric asymmetries. Do we expect the northern and southern hemisphere to look very different, in part because of these effects when we introduce asymmetries?
Yeah, so that's why the area that what I would be interested to get into it, and then I would that was I because I think so I didn't show a plot. Maybe I have it later in my backup. So basically, it's like you see in this plot. This is like the ion velocity, and this is the neutral velocity. The green lines are the ion drifts, and the magenta are like the neutral speed. And what we see that when the solar wind driver is off, and when IMF-BZ turns northward, these neutrals, because they're much more, and they got all this momentum, they tend to drag the ions. And I expect these sort of dragging that is regional to one direction that could create some sort of asymmetries in the thermosphere.
Very cool.
Any others? Jay, you have your hand up, and then Neela, you are after Jay.
Right, so I muted myself. Can you hear me?
Yes.
Okay, Bashi. So, I have a very simple, basic question. It's probably, something that's too fundamental, but I couldn't quite understand. I mean, in your model, you show that the drag was the one that has the biggest impact, yes. And the drag was caused by neutral wind, as I understand, neutral being charge neutral. So I don't quite understand what mechanism that sits behind it that caused the drag from the charge neutral particles.
So basically, what happens is that then maybe that plot was better. So basically, what our neutrals are doing, they're just they're just sitting there, and when these ions are coming, they give these their momentum to the neutrals, and they drag them along with themselves. So that's
so these neutral ion density is very high. Is that what it is? So that as these as these charged particles are coming, they actually collide electromagnetically with these particles, to their nucleus, or
no. There is not it's not like a collision to the nucleus. I don't think it's basically it's just they collide. I think it's it's called through the Coulomb force. Yes, they collide, and they try to drag them towards their direction.
So neutral ion density must be very high then.
The neutral density is high, not the ion density. Yeah, the neutral density
neutral density is high.
Yes.
So they are filling the space. I mean, is it what you're saying, or is it when you say neutral being? Earth's atmosphere?
They're at the 270 kilometer at those altitude. Yes, they are they're very having the space there. Like they have we have lots of neutrons, but the ions, I think they distributed through all the way from these 400 kilometer all the way to 800 kilometer. But the neutrons are mainly sitting at the lower altitude.
Okay, very interesting. Thanks.
Sure.
Okay, Neela.
Hi, Bashi. First of all, thank you for the wonderful talk. So my question is, your this coupling model looks pretty detailed. So can this model be applied to understand the magnetic field interactions on other planets?
This model necessarily, I don't think we still have that capability. No, it's possible, but at this point, I don't think so. Yeah, but I think back source people are, if done correctly, are already doing